welcome to the 77th video on my channel. And today we will be talking about the applications of differential calculus. Now, this can actually get pretty confusing in advanced fields such as biology, etc. And I actually didn't know half of these before doing a bit of research on these. So these are also quite new for me too, and it's going to be a learning curve for both of us. So let's move on to the actual video. These topics get increasingly more complicated as we move on. It's going to be pretty simple, just starting with rate of change, and then it's going to start by then it's going to end with biological interactions, Taylor series approximations, and the sorts of linear approximations. But let's start with the simplest, the rate of change analysis. So this is basically taking derivatives as a good amount at some points and also using the derivative for a real world situation just relating to a certain type of change. Now this is kind of like the foundation for all systems, all things that are using rate of change type. So that's really about it, and that's all you need to know for rate of change analysis. Now, for physics, the most basic application is motion, where the position function is f of t, the velocity is the derivative of that x of t, the acceleration is the second derivative of that, and it's basically just planning motion or parabolic motion, trajectory motion, projectile motion, linear motion, all these types of motions, and the variable t is just time, and x can also be p of t for position. It really changes with everything, and there are a good amount of formulas also relating to this. It also goes the other way with integration, but that will be discussed more in our next video. A quick example is, let's say we have something at position 5 at time 1, and then its velocity is 1. The slope from the xt graph, or the position time graph, would go kind of in the line y is equal to x. But if we say the acceleration is 1, it's going to start going in more of a quadratic curve since it's the second derivative. Another physics application that's used is forces. Now, forces will normally have like electromagnetic forces, gravitational forces, and most importantly, simple harmonic motion. But this uses the most trigonometry, and I would not say uses as much differential calculus, but a very, very solid understanding of trigonometry is kind of understanding for this. Now, the key takeaway is that this analysis is going to be in mechanical systems. Now, for the spring systems, it's less of actually derivatives and it's more of differential equations. For electromagnetic fields, it's differential operators. And for gravitational fields, integration is also quite useful for this and will be mentioned in the next video. Now, this is where stuff starts to get complicated with biological applications. Now, the first is pretty simple, exponential growth model, which uses derivatives, but more commonly differential equations, which was mentioned in the physics application and with the spring systems and oscillatory motion. Now, differential equations are equations that uses derivatives and functions all in one, but that is beyond calculus, and that will come much, much later, after you've mastered calculus and advanced trigonometry and the sorts. The other one is the logistic growth model, which is a type of differential equation, which is not necessarily exponential, where it's saying the growth is limited by different environmental factors. Now, the third topic is birth and death rate analysis, which again uses differential equation, which models population of birth and death. Now, carrying capacity considerations is the maximum sustainable population in an environment and kind of uses a combination of logistic and exponential growth to figure this out. So yes, it also uses differential equations. So the key takeaway from this slide is that there's a lot of biological applications, but they're more focused on differential equations, which also use integration. This is the more complicated for biology, which is interactions, where there's four main types: predator-prey dynamics, enzyme kinetic and reaction rate, SIR models, and neural signal propagation. Now, what this is this is using a special type of differential equation known as coupled differential equations, which is actually quite complicated, and I don't even know much about that. But as for what I know, it's using multiple differential equations to use predator-prey dynamics. Now, for reaction rates, it's more of a logistic growth model or an exponential growth model, and it's a hybrid between the two. With that, I know that much. But enzymes are also a very specific topic in biology with another element, and the differential calculus part is just one aspect of it. Now, spread of disease model is mostly used for like pandemics and population. It kind of is mostly used for modeling. I mean, but how much would it be in the future if this is now and this is in the past? So they create a function using derivatives and differential equations. Then using that, they kind of model the function and they substitute values for a certain point in time, kind of like quadratic regressions for a best fit line in algebra. Now, neural signal propagation is how our electric signals travel through our neurons, and it's using differential equations again for membrane potentials. Now, what they mean by membrane potential is really how much it can propagate or how much it can travel. Now, let's move on to something different, which is economics. Economic applications are a bit different than anything that's done before, as it's actually a bit more dependent on actual derivatives and algebra, less than actual differential equations, and it's kind of like using quadratic regressions or just any type of regressions to model a function instead of using differential equations. So there's this thing called marginal cost, where it's equal to dc over dq, where it's the derivative of the total cost with respect to quantity. Now, for marginal revenue, it's the same thing except for revenue. Now, for the third one, it kind of gives a more practical side to derivative, more than just modeling and theoretical, but it really helps in decision making and the cost per revenue of producing one unit, which is kind of like a mix of marginal cost and marginal revenue. Now, the decision making is where this economic interpretation comes in handy, as it uses this marginal analysis to make decisions on how much production they should do and the cost they should put it at. Economic applications elasticity. This is a bit different, as elasticity is actually also in physics, and many people get confused when I say elasticity in economics. So what they mean implies elasticity of demand. It means how much quantity is demanded responds to how much the price changes. So if the price goes up, would the quantity go up or down? And if so, down or up, how much would it go? Income elasticity is basically how much quantity responds to income changes in the general population or of the company. So, and the third one is for cross price, which basically means how much demand for one good respects to how much demand for one good and another, but also the price changes for that. So these are kind of the three most common things: price elasticity, income elasticity, and cross-priced elasticity, and these are the three main for how much one thing responds to another. Now, the growth rate models again uses differential equations. As I said earlier, these differential equations are pretty much always used for modeling things. Now, optimization problems is more of a pure math concept and less of an applied math concept, but is actually quite used in stuff like these elasticity growth rate models, decision making based on margin, and economic integration to determine how much production and cost they should put it at for maximum revenue and profit. So, Finding the maximum and minimum values is basically what they want to do, and this is kind of where the slope changes for a quadratic function, but it could be much different. Now, the key to doing this is to figure out critical points. Critical points is where f dash x is equal to 0. So if we have f of x is equal to x squared, so then f dash x is equal to 2x. If we set that equal to 0, that means 0. That means the critical point of the function is x is equal to 0. Now, the second derivative test is if we take it again, and this helps us determine whether it is the maximum or the minimum. Maximum or minimum just means whether it's the maximum of the function or the minimum of the function. Now, this last one is a bit more comfortable, and I have actually not really heard of this. It's Lagrange multipliers. Now, this, as it shows, is pretty much for constraints, but it's pretty much not really needed in more basic aspects of calculus, in which you should really focus on is these top three things. This is another economics/finance thing, which is business optimization. Number one, it's for maximizing profit. Number two, it's cost minimization. Number three, it's revenue optimization. And number four, break-even analysis. Now, all these kind of come together to maximize profit and revenue, and that's the whole point of a business, to get as much money as possible. Now, there are, of course, other goals for business, as for impact in your community and such, but if we're just talking about money, these are the main things you need to focus on. Now, determining the point where revenue equals cost is actually really important, especially for startups, which are companies which haven't really made much profit, but they're still in their little startup phase with their still idea and their prototypes. They might not be very big, so this is really important for them to figure out how long it would take and what changes you can make to make sure that we can get as much profit as possible. Engineering design optimization is one of the more complicated ones. The first one that it talks about is structural design for maximum strength. Basically, what it's trying to do is we're trying to use calculus, like differential and integral calculus, to determine the optimal shapes and the optimal configurations of those shapes that make sure that the structure is as strong as possible, while making sure we don't use so much materials, because it's not really worth it to just have a huge steel block to weigh something down, when really we could have a more focused, concentrated shape with a denser material, so it would end up using less material and thus making less cost. The second one goes hand in hand with the first one, where we're trying to use the amount of material, but still making sure we have required performance and maybe even going above and beyond the performance with the material usage minimization. Now, the third one is to really optimize how much strength the material has, to how much weight it has, and sometimes this involves using materials, which is the other half, but also differential calculus and optimization using different functions. The last one is probably the most related to differential calculus, which is energy efficiency improvement, which is really related to optimization problems in pure math. So what we're trying to do is we're trying to minimize energy consumption while doing the same, maximizing performance outputs. Now, resource allocation optimization goes hand in hand with this slide, especially the second point on this slide. Now, the first thing that it says is transportation and logistics. What we're trying to do is we're trying to minimize least shipping costs, least shipping time in all our networks. It also uses the same optimization problems, but it also uses other aspects as like delivery scheduling and fleet management, which could use not just calculus but other aspects like algebra to figure out time. The second is supply chain optimization, which is really linked to the business optimization. Not just these four, but yes, this is actually very important also. The third one it says is portfolio optimization in finance. Now for this, the resource we're talking about is our capital or cash. what we're trying to do is we're trying to make sure returns are as much as possible while making sure there's not as much risks. Kind of like what a lot of people on YouTube are trying to do, and a lot of people on YouTube are trying to teach you how to do this with stock portfolios, bond portfolios, crypto portfolios, and much, much more. Now, as it shows here, there's a lot of pretty common stuff like risk management and investment diversification. The fourth and final thing that shows here is time and resource management. So if we have limited resources, how can we allocate the best for the maximum outputs and the minimum cost and the minimum resource use for better scalability? And this is a lot used with project scheduling, resource leveling, and capacity planning. Now, the way you might be thinking, how does calculus come in handy for this? Well, the way calculus comes in handy for this is again through the modeling of differential equations and the optimization functionings to see how much capacity we have, how much resources we have, and after that, modeling teams can make sure to work on it and for it to have a better output over. Now, this is another pure math technique, which is approximation techniques, which are specifically linear approximation techniques. So what we're trying to do is we're trying to use the tangent line at a point to approximate the nearby function values. So what it says here is formula for linear approximation using the derivative at point A. What this formula is, f of x is approximately equal to f of a plus the derivative of f at a times x minus the a value. Now, for the third one, it's saying how do we estimate the amount of error that there is, calculating the potential error in linear approximations. Now, this is more of applied mathematics as it's involved in physics, but the fourth one talks about small changes in physical systems, in maybe heat systems or mechanical. Now, this is another approximation theory technique, which is Taylor series. Now, I wouldn't really call this differential calculus, but this is more advanced differential calculus used in combination with integral calculus. Now, Taylor series are a specific type of power series, and power series are a specific type of infinite series, which are a specific type of series, which are related to integrals. Yes, I know that was a lot of series in one sentence, but I had to get it all out and tell you what it really was. So, there are higher order approximation using multiple terms, and accuracy increases with more terms, and the Taylor series formula is actually very similar to that, but it goes exact as n is equal to infinity, but for specifically functions called analytic functions. The third type is error estimation, and the fourth type is applications in computational physics. Basically, if we're trying to use computer algorithms or computing the amount of particles in a quantum situation. Now, it says accuracy, it says essential for numerical methods, but sometimes it's not very accurate, but sometimes it is very accurate. It mostly depends on what you're trying to do. The last thing is numerical methods. Now, numerical methods are more of a pure math thing, but there are a lot of applied math things too. So, the four major stuff is the Newton's method for finding roots of a function, the gradient descent and optimization algorithms, which is kind of to use gradients, which is a topic in multivariable calculus, or calculus 3, which involves multiple variables but still has an aspect of differential calculus, but you're trying to optimize computer algorithms. The third thing is we're trying to analyze sensitivity in engineering for different structures, and the fourth thing is perturbation theory in physics. Now, the fourth one is, now this is actually, I'm pretty sure I have absolutely no idea what this is about, but it's basically a specialized type of theory which relates to different types of mechanical systems, especially oscillating systems. Now, all of these are called numerical methods. So, to wrap everything up, a lot of these are dependent on algorithms and optimization and modeling using differential equations. So if you have to take stuff from this video, the three things I just mentioned above would definitely be what you need to take from this video, and that differential calculus is useful in ways you don't realize. But what's more useful than the actual material and its application is how you learn it and to stick with something and practice anything, which is going to be useful in life. So that's what I'm really trying to teach you on this channel. So thank you so much for watching. See you in the next one, and bye-bye.